Right. And that should help. Yeah, in addition to this chunking, we also have two special cases, just to handle all of the edge cases for nice splitting. Anyway, this has some bugs that we have to debug, so let's do that now. Okay, we should be up on YouTube again. Okay, the debug build takes a lot of time. I will have to debug this. I think this is because we are generating gigabytes of debug symbols that linker has to process. I used to generate them into a separate file, but many debugging tools do not support split dwarf, and they were giving me issues. So I had to revert this, so now the debug builds are super slow again. I don't need this log. Okay, this is debug build. The only thing that debug build should do for us, it should crash. That's nice. That's nice because now I want to start it using with a debugger attached. So that now, instead of just crashing, it should also tell us where it crashed. We had some stream disruptions so far. I actually expect more today because there have been a power outage this morning, and power outages don't like to come alone. So they may be like 1 or 2 minute break in the stream. I don't know if this happens or not. Okay, and we should crash in a moment. Here's an example sequence. Okay. Okay, so we are passing the right index, which is way too high. Timestamp gaps has only 4800 elements, and we are asking for this index here. Where do we do this? In update, of course. Parent 3, I6. So this is concerning to me. Let me see. So index number 6 in our binary tree. So we have 0 at... Actually, root of the tree in our case is 1, 3, 5, 7. This is the current value. Okay. I know how to fix this. If node equals n minus 1. So I'm using a trick. This is another thing that can be a little bit confusing. So when I'm initially constructing the tree, I do not want to fill it with any guard values, because guard values, they have to be checked for on every access to the tree. So instead of putting a guard values, I would rather fill the tree with just some fake data. Fake data that still makes the tree work. So this is an example. Okay, should be good now. So let's stop it. And try running the release build of Automat. Still error. Okay. Let's try debugging this again. I think this is the same issue. I don't know why it happens. Now the tree should be filled with reasonable values. And it should crash in a moment. There we go. Again, the same situation. Okay, this tree of sibling is actually... Sibling is just outside of N. How did this end up here? I mean, the tree is massive. Okay, probably shouldn't print it so carefree. This I here, 3096. Okay, so we have this choose better. I was actually wanting to update this algorithm anyway. So that, because currently the update function allows me to update one element in the tree, but those trees, they have this property that it's more efficient to update many elements at once, instead of doing them one by one. Current I plus 8192. It's in 0. Okay, stop. Let's try the release build now. Yeah, I think this the stuff that I've done here didn't make much sense. Now this should work. I initialized the tree wrong. Okay, we are not crashing. Fantastic. Yeah, the splicing algorithm is now pretty much perfect. You can see that the displays are allocated exactly around sections where there is something interesting happening. So this movement up is one section, then movement down And when I'm moving my mouse, I deaccelerate at the top and bottom, so it naturally creates spacing between those movements. And there was another up and down. This spacing was just at this zoom level. It was not enough to cause a split, but if I zoom in a little bit more, you can see that it splits here. Here I have another fun section of left and right movements that when I zoom in close enough, they should also be split into meaningful. This movement right, movement left, right. This movement left is actually shown on two displays. Apparently there was a gap here, sufficiently large to split it. And then movement up and left. Here, another case. This is just split into multiple displays because even though it's one continuous movement, I guess one display would be a little bit too messy. It's good to split those long mouse traces because they can self-intersect and be less readable. Yeah, I can play it. So you can see that my mouse moves by itself, following those mouse traces. I could optimize the update now. But stuff that I have in the small bug fix is worth submitting. It's probably not that important. Okay, so we finished the debugging. The main thing I wanted to do today was to change the mouse traces, how they appear on the time strip. They are using this black display, which is, on one hand side, it's nice. It looks very readable. I can clearly see what the mouse is doing here. But it doesn't quite fit the style of this timeline track. So this is what I want to fix now. I would like to make it to change the color of this thing. So the mouse traces, they should look like drawings. So probably the lines should be black, right? Because when you draw on paper, it's usually black. It could be blue as well. or any color typically associated with drawing. Or actually blue is a good one, a deep blue color, yeah. And the displays themselves, they should be not black, they should look like grid paper. Grid paper is rarely black. Okay, let's try this. So we have this pixel grid SKSL. This shader, it's a super simple shader. It takes two grids and it combines them. But I would like to combine them in a more flexible way now. Okay, so we'll have our background. Then we will have color for grid 10. And grid 100. And those will be vec free. And I have this clamping here. It would be nice if shaders had some default values for uniforms. So how our shader is going to look like. we are going to use background color. Or actually we will mix background color and grid 10, yes. And this we will mix with actually no, there is small issue is how we actually should combine those colors. By combine, I mean right now we are adding them, like one channel is used for Y, one for X. And let me see something. So if I skip all this, what will happen if I just add transparency to the background? So this is going to be maximum. Can I have more? I need to have more maximums. Just slightly different alpha value. Okay, now we have something that looks kind of strange because it's very dark. When it's transparent, it should be getting brighter, not darker. Somehow it works fine here. I could change the blend mode. Probably read about those blend modes. I want to use alpha. Plus is a wrong blend mode, definitely. Let's try screen. Screen often produces interesting effects. I think something like difference would be good. It's difference or exclusion. So I have a very dark overlay. Or multiply, yeah. This isn't very readable now. Let me remove this blend mode for now and let's play with this alpha value. Alpha is the maximum of those. So maybe this is what I could minimize. Yes, and then I can keep those minimums here. Since it's transparent anyway. I think the red part isn't very red. And the green part isn't very green. And it seems to have this black edge. Let me grab the old formula. So we can try to create a new one for, like, intended for white background now. So instead of taking minimum of this, okay, now we have a nice red and green. Although the green is very bright. It seems to work on all backgrounds though. Pick a nice color. Maybe this kind of green would be nice. Yeah. color feels nicer, but should be darker. This should make it darker. Skia uses pre-multiplied colors. Now I have to pick this differently. It should fail, I think, right? Okay, it works. This color looks nice. It looks like a decent green now. It's barely visible, but it shouldn't be too visible. The point is not to make it very heavy optically. Okay, around those coordinate axes, I would like to draw some bounding boxes. So 0.3, let's do 0.5 maybe. Should be more visible this way. Could be even more visible. 7. Okay, that was nice. I didn't have to parameterize the shader in any way. It's just a slightly different color in alpha. Brightness seems about the same now. Here they actually add in the cross sections, I think. Yeah. So somewhere here there was clip. The color of this paint is going to be, it should be grayish, something like that. Stroke width, I will leave it at 0. Because I want a single pixel outline. Or maybe I could use this. Yeah, I think I will use this thing. It feels blue, right? This edge. Weird. Okay, I wanted to increase the width of this thing. So creating border paint here. Yes. Actually, not one. One is going to be way too high. would like to increase the width of this outline. First of all, it's too heavy, so it should be brighter. Can I edit it here? I don't have a convenient editor. Fire up Krita. Krita should have something. Yes, it is bluish. This is why I thought it's blue. So it should be brighter. And maybe... yeah, less saturated. Color like this one, maybe. Okay, looks better. The next element is probably width, and I think it should not be blue. I will make it neutral gray. The color is pulling too much attention. Something still feels off about it. Okay, I will change the color of the mouse trace now, so that it's visible. Trail, exactly. Trail paint should be, let's make it deep blue. This trail is, by the way, the only thing which, in terms of complexity, like algorithmic complexity of drawing this path, the fact that we are drawing each point makes our algorithm linear. And even though the display chunking is logarithmic, the path itself is still linear, so we would still have some more features to properly chunk this path dynamically if we want to have a fast algorithm for drawing arbitrary length paths. But now this track, it looks more like a drawing. So there are a couple other things. Let me switch to Emacs. So the colors are nicer, but I also want to change this segment color, maybe something that would match our deep blue color. And then probably we should separate a widget from the track object, because track object could be, it's a separate thing in Automat. This is very important for optimization, because if we have separate widgets, they can exist without any computed data, they don't need it. Only widgets, when they are displayed, need to store this extra information. Anyway, I will be right back. Okay. This keeps moving. It didn't crash. Such a long time without crash. Okay, this event marker color. Where do I draw it? This horizontal segments. Vec to paint. Will have the same color. I'm thinking of maybe making it maybe I could make it as white as the whole track and very transparent. That would be interesting. Oops, was the wrong one. Let's try this. Oh, actually, I should use this paint, right? If I zoom in, this is how it looks now. I have another idea. Maybe it would be nice if it was drawn like on top and bottom, above and below the display. It should be possible. Here I have these draw displays. I could either overdraw.
I have started to dig into your run. By script.
URL.
Hey. What do we have here? Logging. I never used logging, the Python logging functions. Python has some logging package, right? It's not yours. Yeah. I wonder what are the benefits of this module. Slang format. Yeah.
Quick debug logging.
I like that fact that Python is probably like the easiest build language to understand. Way better than CMake. It's something that you just know anyway.
I think Python should be default shell.
And that would be nice. Some things would be trickier. I mean, the subprocess module could have some improvements to make it more convenient. But yeah, Python shell makes sense. I think I've seen at least one project like that, where it was Python intended to use as your interactive shell.
TTS on Windows 11. You can use Python as default shell.
The same way as Ubuntu, right? If you install this Windows for Linux, and then you can also set Ubuntu as your default terminal shell.
I think Quake uses Lua instead of Python.
Lua is also nice. It also has this object-orientedness as a key element of the language. By the way, did you try to run Automat build after I fixed the Windows SDK installation? I wonder if this, if the issue went away. Yeah, this is a nice way to define paths. It's usually good to put some kind of resolve here, path.resolve. Because sometimes the path to script, actually I'm not sure if Python can mess it up. But if it contains this, home directory reference or funky links, it's good to clean them up. This cache class, it reminds me of default dict. Oh no, it also has read and write. Okay. Should be the same thing here. See now. Okay, the idea here is that we have those ticks on top which show us where the events are located. If I select any section and zoom in here, for example in this first motion, I can see the individual ticks. Maybe I can make it even more pronounced. It's just on the edges, so it can be very... a little bit heavier. Cool. I like the new style. In terms of our to-do list, the stuff that we've finished. This is finished. Okay. There is some thinking I need to do now. Indicator should highlight the whole vector, yes. So the The problem is that the circle that I'm drawing right now, it highlights the destination point of the next movement, but each movement is actually a tiny vector on this track. It should actually highlight those tiny vectors somehow. If I zoom in closely, it's easier to see them. They crashed. It's interesting. Zoom in again. Here is, for example, a single event. This is a single kind of jump, atomic jump. If I move back enough, should see some other vectors, slightly more interesting. This one is slightly diagonal. I will run this under debugger. I want to catch this crash. It seems to happen every now and then. So let's think about this. Now when it crashes, we should at least, it will be way slower, or less nice to work with, but at the very least we should get the stack trace when it crashes. What could I do here? So I think if I draw this circle behind the line, that's going to be definitely the first step. Maybe I should draw it as an arrow to show the direction, that it's a vector. Okay, so playing this bug isn't going to crash anything. I need to play with zoom that was causing some issues before. Of course, in debug mode nothing crashes when I want it to crash. Last time it crashed when I was just scrolling like that. And this is a nice place. Here we had 4 events, but they are all separated by less than 1 millisecond. It's probably operating system receiving multiple events and then dumping them at the same time. Because normally there is a difference of exactly 1 millisecond. 6.4, 6.3. Doesn't matter. Okay, I will try to change the drawing order now. Okay, so we can just draw this right before paint. Oh, I see. The issue is that the radius, the coordinate space uses different space. I think this should be doable. I will just have to play with radius size. Okay, we don't need this. So now we are drawing in the kind of pixel space, like emulated pixel space. Here you can see, yes, there is a pixel. It's only going to become more visible if I zoom in closer. The fact that it's changing size is probably wrong. So maybe I should divide this by scale. I think that might help. This is radius, and it actually looks reasonable. Let's see what happens if I do some zooming. Again, crash. Why doesn't it happen in debug mode? This is probably some threading issue. And this is actually a perfect example of the issue. So I have a display that spans like 5 points, and I would like to highlight the segment which is currently relevant. Like this one. It's another one here, another one here. So this would be only this diagonal movement, only part of this horizontal movement, another. Maybe I could draw this in, I don't know, maybe white. White feels appropriate. I actually have an idea. I could draw this circle over the trail. But the current section I could draw with the trail paint again on top of it. We need 2 points. I will run release mode again, it's going to crash, but I have to track this bug somehow. It only seems to happen in release mode, so I have to somehow put symbols there. I have that special build mode, fast release. I mean, there is this mode for debugging, right? It would be nice if I could draw a capsule. That's kind of what I want here. So now I can highlight this section that I'm drawing. There is a way in Skia to convert drawing operation into a path. Could try to convert this into a path. It's trail paint. Path hoops maybe. That's not it. Okay. Okay, this is a rather longish chain of operations. I'm just trying to create a simple outline path. This will be stroke, and this will be stroke and fill, yep. Okay, I must have messed up the rotation, I think. I put semicolon here and get rid of this rotation. That should draw reasonable rectangles. Oops. I don't see them, unfortunately. Let's go through the... This is left, bottom, right, makes sense, and top. Okay, so it looks like a circle, but it's actually a rounded rectangle now. It should become apparent when I zoom in. It's not rotated yet properly. Let's fix that. Okay, this syncos, it allows me to avoid the trigonometric operations. I don't need trigonometry here. Okay, let's zoom in now. I think I need to change the x and y. Yes, it's sin cos, not cos sin. Cool. Now, each of those points can be seen here. Yeah, just a simple highlight. It's crashing very fast now. Maybe I can catch it finally. That would be nice. So slow. So now it's possible to finally distinguish those segments, like this one. This horizontal line is composed of two segments actually. Maybe if I just keep zooming in and out, dragging this around, eventually it will crash. I don't know how to make it crash actually. But I think we just did it. This point is done. It highlights the whole vector and it's drawn behind the line. I think all of those improvements are pretty much done. One more thing would be to split it like I have here. Split widget and an object. Something we should probably do. We'll do this right away.
How to make it crash. Derif null titar. Simple as that.
I wish. I mean, crashing is easy. Crashing and getting a call stack, this is hard. I can also debug a fast build, so maybe I can try with that. This is not a debug version, so it should run like way faster than the debug. But should still crash. Record the macro. So this is our tricky macro that we have recorded. We can even close it, but we have a... It's not the crash I'm looking for. So I saved it into a file. So it should be easier to reproduce now. And I think the crash comes from just panning around or changing the zoom level. Something like this seems to be causing the crash. So maybe I will set up something that will press the mouse button, and after mouse button is pressed, I will start this movement. This is Automat debugging itself, kind of. I'm setting it so that it will play with its own zoom level. So now it's moving this scroll bar by itself. And it's doing so in a loop, so eventually it should trigger a crash. I have no idea. Now it doesn't want to crash. Actually, I had a video I wanted to watch, so maybe I will grab some food and yeah, in a moment I can watch it, and Automat will try to trigger the bug in the background. What could have caused that bug? You know what, let me pause it. Stop. Actually, when I pause it, do I get stack traces? Yeah, it looks like I do. Yeah, very decent stack traces actually. Shocking. Do I even need the debug build at this point? Huh. Okay, let me check what was the video I wanted to watch. It was something about atomics. This one.
Hello.
So, I will be right back. now the setup. So I suspect that maybe something wrong is with the state of the release automat. I will copy the state over. I will rewind this a little bit to YouTube.
So C++20 introduces some new scalable synchronization primitives and some other enhancements to the standard library. So I try to use as much C++20 in this talk as possible, including ranges. Most of the range facilities are in these two embedded nested namespaces, std : ranges and std : views. So I'm just going to use these two namespace aliases so that everything fits on my slides. And so when I was thinking about how to make this talk, originally I was just going to go through each feature and just
That was kernel having issues with thread scheduling, probably because of NVIDIA drivers.
Thought I can actually make one big example and use every feature in that example and just sort of tell one continuous story throughout the entire talk. So I'm going to attempt to do that. And the example I'm going to build for you is a little tasking runtime. Before I worked at NVIDIA, I worked on an open source parallel runtime called HPX. So this is sort of going back to my roots. So there's four key elements that we need for a tasking runtime. First of all, we need some set of worker threads that are going to actually execute the task. So we need some execution resources that are going to actually run the work.
There we have a crash immediately. Nice. This is what I was looking for. So the issue seems to actually be somewhere in the state file, I think. But the crash comes from VK recorder. This is bad because VK recorder is actually very, very simple. It just executes recordings. Win playback. It's failing within playback. Okay, the timeline. Has issues playing back its recording. And what specifically within timeline is causing issues? The dimensions look good. It's fairly deep. Auto layer for image filter. Do we have? Somewhere here there should be timeline draw. Timeline has a very complex drawing. It's 500 lines, essentially. And we have some image filters here. I think textures that we are using are image filters. So we have In each filter we have blur. I have quite a few blurs. Tons of blurs, actually. Eval blur, blur 1D, render blur, snap special. Actually, we are on the previous line, on this 1, 2, 3. It could be that some of the resources that Skia is attaching when recording commands are not being kept alive. Because there is... Actually no, this fault address is very strange. 98 hexadecimal 100. RBP is stuck, so this is some address on stack, and R11 is unknown error or what? Strange. Oh, it's because R11 was overwritten by something. RAX. So this value was, this hexadecimal strange value was in R11. Let's look at this function in Skia, graphite draw pass make. This happens right after get uniform something over right whatever. Right after this get uniform writer. Have this right. And I guess this right uses memcopy. Let's see if this line was changed in recently. How do I activate blame? This hasn't been touched in a long time, except this change, like almost a year ago. I wonder if my version of Skia has it included. Drawpass.cpp. Let's see. If my version differs, then maybe I should just update. Three 7.7. Get uniform writer. The most recent version seems to be slightly different, but it seems like it's in different place. Maybe I should avoid blurs then, if that's the issue. That would be a suboptimal solution, but it seems the issue is not in our code. The issue seems to be somewhere in how Skia passes, how Skia creates this blur filter. Oh, and the stack can have actually a very strange structure. Sometimes compilers can put the stuff on stack which is supposed to be called afterwards, like return-oriented programming, kind of. But still, the leaf, this is where the error happens. Okay, I have 13 blurs here. So here's a draw path with a blur. Okay, so this is drawing a very subtle black shadow inside, I think. And I have this inset. It's a blur filled with gradient, which they both are. I think I could just write a nicer shader that would avoid this blur. It's definitely going to be faster as well. Okay, we have those two blurs which are blurring large gradients. And we have this window shadow. Wavy paint. Okay, so this section, this is also blurred. A lot of things to check. The interesting thing is, why did it happen only when I was having this specific state file? Something about the number of tracks must have caused the problem. So for fun, let me disable the blurs. See if it will still crash if I play with it now. I think I may be pushing this blur implementation a little bit too much, because I'm rendering everything at a very, very fine scale. If scale has any heuristics that assume that a single unit is equal to 1 pixel, it's going to cause issues. We still have crash. Time to debug. So I removed all of the blurs, but it still has issues. Okay. And it seems like just navigating through the timeline was enough to trigger the problem. Set up the debugging thingy. Yeah, that's fine, that's fine. Okay, stop for a moment. This can take a while. I don't know if it will crash right away or not, so it doesn't hurt to cue something play in the meantime.
Queue and execute it. Then we need some sort of termination detection mechanism. This seems like it might be like a little detail or an afterthought or something that's, you know, doesn't really belong on the list of major features of this tasking runtime, but it's actually pretty tricky to get this part right. And then we're going to build.
That was fast. Again, crash in VK recorder. What was the widget right now? It was key label widget. It's almost the same, actually, this stack trace. Again, address not mapped to an object, the address is very, very low. This key label is actually a very simple object, it just draws a piece of text. So there must be something in those recordings. No, the error happened at a different point. Before it was happening during playback, now it happened in this snap. But the final pass, I mean, the point where crash happens is the same. In draw pass make.
Mastermind says.
Cool hairstyle, dude.
Hey. I could try updating Skia and seeing if it will work. Has there been anything interesting recently? I'm not having high hopes. I'm using 136. The current version seems to be 139. Probably good to update in general. Let's see. This will take a couple of minutes, compiling everything, I mean. Switch to 139. Skia is a pretty heavy library, so even deleting it took a while. So it's going to take a moment to fetch it. Okay, let's check this. Third-party Skia include GPU, graphite. Yeah, I have a patch that was adding a missing include somewhere here. Yeah, include string, which doesn't seem to be necessary. I will remove these patch sources. Okay, coming back to this.
By figuring out how we're going to organize our pool of worker threads. So as I mentioned in C++11, we have stood thread, which is a low-level abstraction for creating threads. So if we need like a bunch of threads, we can create something like this. So this is just some thread group class. It's got a vector of stood threads. And in the constructor of this thread group class, I give it a count of how many threads I want. And then I give it one invocable.
This IOTA is interesting.
An invocable is a C++20 concept for some object that can be called. So
to me, it's almost always better to just go from I0 to IN using standard for loop.
The count that I specified here. So this is pretty straightforward. But even this straightforward code.
I wonder what's the advantage of having IOTA instead of manual.
The bug is that when you destroy a stood thread that has not been joined, stood terminate is called. So if we go and we create our thread group class right here, we say we want 6 threads. We're going to give it a function that just increments this atomic count right here. So what's going to happen is when this thread group object goes out of scope at the end of this block scope right here, it's going to be destroyed, and it's going to destroy all of these stood threads. And we haven't joined with those stood threads, so stood terminate will get called. This is sort of unintuitive. Usually in C++, we expect things to act with ray semantics. So, you know, they acquire their resources on creation, so the thread gets created when you construct the stood thread object. And you would expect that when you destroy a stood thread object, that it cleans itself up nicely. Stood thread, unfortunately, doesn't do that. So we can go and add a destructor to our thread group class like this that just calls thread.join on each one of the stood threads, and like that's fine, but we have to remember to do this. And remembering to do this is kind of annoying. So we're planning on using our thread group to implement a task pool, as I mentioned. That means that each worker thread is going to be executing some loop that processes work continuously. So we'll use this little dumb function as a sort of little placeholder for what the thread function will look like, where we're just going to be in some loop that's going to be like while true or while some termination condition, and then we're going to execute work. In this case, we don't have any work yet, so we're just going to increment this atomic. But we have to come up with some way to figure out when the workers are done. How do we, signal to them that they need to exit this loop? So we have to build some sort of side channel for that if we're using stood thread. We could use atomics to do this. So I've created some stood atomic bool here that starts off initialized to false. And then inside of the worker thread function, instead of just while true, they do while the atomic is not, while the atomic has not been set, we're going to keep incrementing this other atomic. And then at the end here, to actually signal to all those threads that I created that, that I want them to be done, I just store to this done variable right here. So again, you can do this. This is like somewhat straightforward, but you have to remember to do this. And if you don't, you might end up deadlocking here because your threads might just end up in their loop forever, never receiving their signal. So in C++ 20, we have stood jthread. The J stands for joining, although it is also the
There's a lot of complexity there related to
last name of the author who,
sleeping threads. When any of those threads tries to go to sleep,
either way, either being
waking them accurately, this is tricky.
And jthread joins in its destructor. So it does not have that problem that std_thread has, where we have to remember to add a destructor to our thread group class to explicitly join with each one of those thread objects. And std_jthread also has some other enhancements. So it's just like std_thread, except if the thread is joinable, it joins with it instead of calling terminate in the destructor. And it also has a nifty interruption mechanism, which you can use to signal to a std_jthread that you would like it to stop doing whatever it's doing. So we can do that by instead of the thread functions for jthreads, they can take either a just regular invocable that takes no arguments, or they can take an invocable that takes a stop token. And a stop token is a thing that you can query and ask, hey, have I received a stop request yet? And then you can, like, once you receive the stop request, you can do whatever you want with that. Presumably, you want to honor that request and exit, but threads, it's optional. You don't have to respect it. And then you can also request that a thread stops. So I've added this request stop member here that just iterates through all the members of this vector and calls request stop on them, which will then set the stop token that's been passed into each one of their worker thread functions. It will signal to that stop token that a request has been stopped, that a stop request has been sent. So std_jthread supports interruption. Std_thread takes an invocable that takes no parameters. std_jthread can take an invocable that either takes no parameters or that takes a stop token parameter. And you can, there's a couple different parts of this stop token machinery. So you've got stop source, which is sort of analogous to a promise. It is the producer of stop requests. It owns the shared state of the stop request. Then you've got a stop token, which is a handle to a stop source. It's the consumer. It can only query whether or not a stop request has been made. It can't make a stop request. This is the consumer side that the worker thread receives. And then there's a callback mechanism called stop callback, which you can use to, it's sort of analogous to future then. You can use it to register invocables that you want to be run when you've received a stop request. And then on std_jthread, you can query, you can get the stop source associated with the jthread. You can get a stop token associated with the jthread. And then, as I showed, you can request that a jthread stop. So this is a useful mechanism because it means that you no longer have to build your own interruption or termination mechanisms. There's also some support in the standard library synchronization primitives for stop token. Unfortunately,
the problem with stop tokens and stop sources is that there is no API to wait on multiple of them. If I have a stop token and some atomics or mutexes or some other operations, and I want to just wait for the one that happens next, there is no API, unfortunately, for that. And because of that, atomics are still king for stopping threads.
Not in some of the...
I mean, I would appreciate if he, in this presentation, actually warned about this.
New facilities that I'm going to show you today, but hopefully in C++ 23, we will fix that little oversight. So condition variable condition variable, any actually, has a few different polling
Yeah,
APIs.
condition variable is one of the nicest APIs in C++. I mean, not nicest APIs, but it allows you to do fun things. Condition variables with this mutex-like behavior, like you set up a condition variable on top of a mutex, and it very clearly separates the point in time where your thread has access to the state and other threads, and you can kind of flick back and forth in them. And it's a little bit weird, but allows you to do fun things.
And we've added some new ones that support stop tokens. So the way that these work, like this first one right here, this wait until, where I give it a lock, a predicate, that's all normal and what we're used to. And then we give it a stop token. What this does is it will wait for the predicate to be satisfied until, but it will exit early if a stop request has been made. This is quite useful because usually with these hand-rolled interruption mechanisms like the stood atomic one that I showed you before, you have to actively poll on the thing. With this interface, you can just tell the underlying system API, hey, I want to wait until...
Atomics have notify methods. So on atomics, you don't need to poll. You can just block, and another thread can just notify one of the blocked threads. It's not entirely...
until this condition happens or until I receive an interruption request, and your platform can do something more optimal than just polling if it has that option available to it. All right, so now we're going to replace our atomic variable that we were using for signal and termination with a stop token here. So we just changed the thread function to take a stop token, and then in the body of our thread function, we just do while we've not received a stop request, we go and do whatever stuff we're supposed to be doing. Okay, next let's build ourselves the work queue. And again, this work queue is going to be filled with tasks, and each one of the worker threads will continuously pop items out of this queue and execute those items. So we are going to build a concurrent bounded queue. So by bounded, I mean this queue has at most queue depth objects in it at any time. The alternative design is an unbounded queue where it can have any number of objects in it. The trade-off is with a bounded queue, you have a fixed memory footprint. But you potentially have to block if the queue is full. Whereas with an unbounded queue, you never have to block to insert into the queue. But the memory footprint of the queue will just grow until you run out of memory. If you're submitting way more work than you're processing, the queue will grow very quickly. So the reason that we're using a bounded queue in this demo is not because of a conscious choice of me feeling that it's better. It's just because this is the canonical example of how you use semaphores, which is what we're going to talk about next. So this concurrent bounded queue, it's got a stood queue of items. Pretty straightforward. Then it's got a stood mutex that protects access to the items because we have multiple different threads that are going to be pushing and popping items out of this queue. Then we have two counting semaphores. And counting semaphores are sort of like a generalization of a mutex. A mutex controls access to to an entity, and it allows at most one thing to have access to that entity at a time. A counting semaphore allows up to n things to have access to a resource at a time. So it allows us to manage a shared count. So we've got two different counting semaphores here. We've got one that's called items produced. This is going to keep track of how many items are in the queue. And then we've got remaining space. And remaining space is going to keep track of how many entries are left in the queue. How many more things can we insert until the queue is full? So items produced will start off at 0 because the queue starts out as empty. And remaining space will start off at queue depth because initially we can insert up to queue depth items into it. All right, so the queue has an enqueue method, a dequeue method, and then a try dequeue method. We're going to just walk through how those work. OK, first I'm going to talk a little bit about counting semaphore. So counting semaphore looks like this. It has a release method that lets you add some count to it. So if I release 5, that adds 5 to the count of the semaphore. And then it's got some acquire methods which take 1 count from the semaphore. So we've got our typical blocking acquire. Then we have a try version that polls. Then we have a try version that polls with a timeout and both a relative and an absolute timeout. This is somewhat similar to wait APIs on condition variable and various try lock APIs on mutex. The counting semaphore, you tell it at compile time as a template parameter what the maximum possible value is that you might want to instantiate this with. This allows implementations to pick optimal implementation strategies. For example, you might have an OS primitive to implement counting semaphore if you know that the count will never exceed 32 bits. But if you need a 64-bit count, you might not be able to use that operating system primitive. You might have to use some other slower mechanism. All right, so that's counting semaphore. First, let's look at this little pop helper function that we have. It's pretty straightforward. So all that this does is it acquires a lock on the items mutex, and then it pops an item out of the stood queue. The only reason that it looks a little bit complicated is because the pop interface on stood queue is a little bit unfortunate in that it doesn't actually return the item that it pops out. So first you have to get the item, which we do here by doing a stood move on the item at the front of the queue. Then we pop it, which takes the empty item out, and then we return the thing that we popped out. So yeah, so just explain. OK, then let's look at our enqueue method. So our enqueue method, we take some value that we want to put into the queue. The first thing we do, we have to make sure that we've got space in the queue for it. So we attempt to acquire on the remaining space semaphore. And if the remaining space semaphore has no count, then this call will block until somebody releases some count to remaining space. Then we go ahead and lock the item's mutex, and we insert the item into the queue. Now, you might notice here we're using both a mutex and a semaphore. That's because the semaphore alone does not protect access to the queue. For example, if we have 8 remaining space in the queue, 8 different threads might at the same time concurrently be calling in queue and concurrently acquire the count there. So those guys all have gotten a count. They know that there's space in the queue for them to insert their item, but we still need the mutex to ensure that they don't try to add the item to the mutex to the queue at the same exact time. So then after we've added the item to the queue, we want to go and let anybody who's waiting to dequeue an item know that we've added a new item. And we do that by releasing a count of 1 to the items produced semaphore. So now let's take a look at dequeue. And dequeue is pretty much just the inverse of what we just saw. So in dequeue, we go and attempt to acquire a count from the items produced semaphore. And then once we've done that successfully, we pop a element from the queue. And remember, the pop function we looked at before does the locking for us. And then now that we've taken an item out of the queue, we know that we've just freed up space in the queue. So we can release a count to the remaining space, letting anybody who's trying to enqueue know, hey, there's an entry that you can use. And then we return the thing that we popped out. Try dequeue is basically the same thing. The only difference is instead of doing a blocking acquire here, we do a try acquire. And if the try acquire fails, we just return an empty optional here. This try dequeue returns a std optional instead of just a t. And if it succeeds, then we just do the same thing as before. We just pop it, and then we release to the remaining space semaphore. And this one is useful because it's a non-blocking API. OK, so this is what our concurrent bounded queue looks like. So let's talk a little bit more about this std mutex. So std mutex is a little bit of an unfortunate choice for us to use here, especially for something like a task queue, because std mutex is fairly heavyweight. On most platforms, std mutex will use some sort of operating system mutex implementation, which means that calling it might involve a kernel call. It might sleep your thread. It's potentially quite
on Windows,
now,
it's something like 60 or 80 bytes.
Implementations will have a fast path where they'll use atomics to try to ensure that if the thing is not contended, that they won't have to actually make an operating system call. But this is almost always going to be an OS primitive, and it's going to be fairly heavyweight. So it would be nice if we can use something that's a little bit lighter weight, that'll have lower latency and it won't have as much overhead. So one alternative is that we could build a spin mutex that just uses std atomic. So here we've got a std atomic bool, and the implementation of our lock function is just going to be a while loop that constantly tries to exchange true to this flag. And if it succeeds, then it has acquired the lock. And then the unlock function is just going to store false to the flag. And that's pretty much it. Now, we could also use atomic flag to implement this. Instead of exchange, we'd use test and set here. And instead of storing a value of false, we'd use clear. Now, the issue with this is while this is very low latency, it is not very resource efficient because we have this while loop right here where we're just constantly spinning and pounding on this atomic. So if a large number of threads are all trying to acquire this mutex at the same time, this isn't going to perform very well because all of those threads are just going to be constantly hammering away trying to acquire this atomic. So this does not perform well under contention at all. So there's some alternatives to this design. You can add some back-off mechanisms. So instead of just constantly spinning on this atomic, you can spin for a little while, and then if you haven't acquired it, you say, well, that probably means that somebody else is trying to acquire it, so we should probably just sleep for a little while. Just go do something else. We're not acquiring this lock, and us attempting to continue to acquire it is just adding to the contention and making life more difficult for everybody else. It's sort of like if you go to a bathroom and there's a really long line at the bathroom and you just look at the line and you're like, you know what, I'm just going to come back later. I don't want to wait in this line. It's going to clear up, and then at some point in the future, there will be less of a line in the bathroom. So this is what a very platform-specific implementation of such a back-off mechanism might look like. This is actually taken from the Linux x86 back end of HPX's spin mutex. So here's what we do. We've replaced our while loop that just spins in the atomic with this for loop here. And it still does every iteration. It checks this atomic. It attempts to set true to this atomic. But we keep track of how many iterations we've been trying. That's this k variable here. And for the first 4 attempts, we just do nothing. We just make the first 4 attempts with no back-off mechanism. So that's this right here. And then after the first 16 attempts, we do some sort of processor-level pause here. So this rep no-op sequence is how you sort of do a very short-term pause on an x86 processor. And when we've done 64 iterations of this loop, then we start yielding to the operating system by calling schedule yield, which on Linux is the way that you tell the kernel, hey, this thread, don't schedule it for a while. Go run some other thread. Defer me for a little while. And then finally, if we've been spending more than 64 iterations, we just go and call nanosleep for 1,000 nanoseconds. So we actually put our thread to sleep. We're just like, we'll come back in a while, and we'll check to see whether we can acquire this thing. So this is a pretty good implementation. But as you can see here, there's a bunch of magic numbers. Like, how did we pick those numbers of 4, 16, and 64? They were just numbers I made up in like 2013. How do we choose these 3 back-off mechanisms? That's just what seemed to make sense. And of course, it's very platform specific. So this is not something that's like easy for you to put into your code base, even though this is a pretty good mutex alternative. It's pretty good under contention, and it's very low latency. So in C++20, you don't have to write this
Very nice
yourself.
implementation.
In C++20, we have a wait and notify API that's been added to atomics. And your C++ standard library implementer, they will go off and write whatever nonsense makes sense for your platform, because they're the right people to be doing this anyways, not you. And you just get to leverage that. So the interface looks a bit like this. We've gone back to just having a while loop where we just constantly try to set this flag. But then in the body of the while loop, we do this flag.wait. And what flag.wait says, flag wait true and then some memory order. What this says is, all right, wait until this value has changed from being true to being something else. So the first parameter of wait is the value that you're waiting for it to change to be something different than that value. And so what this will do is, like, if the flag is set, then it would wait until the flag is no longer set. And we'll know that because somebody will notify us when the value's changed. And then we would wake up and we would continue attempting to set it. So this wait call here replaces that whole back-off mechanism we saw on the last slide. How it's actually implemented, it might be implemented in that way. We'll talk a little bit more about the implementation options in a minute. And then on the unlock side, where previously we just cleared the flag, after we've cleared the flag, we now need to call this notify API. And what notify says, there's both notify one and notify all, is it says, hey, go wake up some of the people that are waiting. So in this case, it says, go wake up one person that's waiting and let them know the value's changed. And notify all will say, go wake up everybody that's waiting and let them know that the value's changed. And this is the version with atomic bool, because this is not just an API on atomic flag. This is also an API on just regular std atomic. So here's what std atomic and std atomic flags wait and notify looked like. It's just this new wait API. So as I said, it takes a value of what value you're waiting. You're waiting until the value changes from that. And then you've got the notify one and the notify all API. And so there's a couple different ways that this might be implemented on your platform. So you might implement it with a futex, an operating system futex. This will work for certain size objects on Linux and Windows. You might use condition variables, OS condition variables. This will work for certain size objects on Linux and Mac. Now, using futexes or condition variables actually isn't that efficient if you just use them naively, because as mentioned before, OS primitives like mutexes, condition variables, and futexes tend to have pretty high overheads. So one thing you can do to amortize those overheads is you can have a contention table where you've got a static table of a bunch of futexes and condition variables. You can use this to basically to optimize the cost of futex notifies and the cost of holding these CVs. You might not use an OS primitive at all. You might use timed backoff, like the example I showed you before of the handwritten version that I had. And that'll work pretty much everywhere. And you could also just implement it naively as just a spin lock, like the first example we saw, and that'll work everywhere too. The performance will, of course, be terrible. One other little atomic enhancement in C++20 is that we finally added a test method to atomic flag. Previously, there was no way to test if an atomic flag was set without also setting it. There was just test and set before. So I don't use that anywhere. It's just a good thing to know. All right. So this is the final version of our spin mutex, but this still sort of has a bug. And the bug is that this is not a fair mutual exclusion mechanism. What I mean by fair is, let's say we've got two threads, thread A and thread B, and thread A starts attempting to lock this spin mutex. It is possible that some other thread, thread B, could come in, and it just happens to win. It just happens to acquire the atomic before thread A. And it could acquire the atomic and then go and do its thing and then unlock it. But this is unfair because thread A started trying to lock this thing before thread B. Like thread B came in cut in line, and that's not particularly fair. Yeah, this is an unfair mechanism. It's good under contention, but it's not fair. And if we care about fair tech, and we might care about fairness. So there's another type of mutex called a ticket mutex, which is a fair mechanism. So ticket mutex, we've got two counts. We're just going to represent them as stood atomics here. We're going to call them in and out. And so inside of the lock on a ticket mutex, the first thing we do is
was implementing version command for my
so we go to
Frogot.
the in atomic,
What I was doing
add
now,
one to it, and we
I
get
have
some
to
count.
commit
That number is our ticket.
semi-borked
And then we go into a
implementation.
while loop, and in that while loop, we keep loading out, and we keep checking whether out has been set to whatever our ticket number is. And when out has been set to our ticket number, then we know that we've acquired the lock. And if out hasn't been set to our ticket number, then we wait for out to change
I'm actually
before we
wondering,
go and check
what's
out
the...
again. And again, we're using the wait API.
Because I saw in your RunPy implementation that you're still deferring to CMake to build the actual app. So what is the value that RunPy brings? Is it just a wrapper around CMake, or does it try to provide something extra that CMake does not?
API here, so we know what value we just loaded. That's the now value, and so we say, hey out, like this is the value that we just saw from you. Let us know when you change from that value.
Command runner brother.
Then in the unlock side, all that we do is we increment the out count by 1. And then we notify anybody who was waiting here. So you can think of this like a ticketing system at a deli counter. You've got some distributor of tickets. That's the in atomic there. If you want to go and order some meat at the deli counter, you go and take a ticket. You get a number, and then there's some sign that says what number is currently being served. And when that sign matches up with the ticket that you got, then you can go and get service. That's how a ticket mutex works. There's one more thing that we can improve here. We don't want these two atomics to live on the same cache line, because that would sort of defeat the whole purpose. We don't want these two we don't want attempts to increment the in atomic to conflict with people who are polling on the out atomic, because we might have a bunch of people that are polling on that out atomic. And we want it to be very quick for us to go and get a count from the in atomic, because there's no reason for it to not be quick. So what we can do is we can align these atomics to a suitable size so that we know that they won't end up on the same cache line. And there's a C++17 feature that makes it easy for us to do this. It unfortunately has quite a long name, which is stood
The keys I can
hard-code
hard-code
interference
commands in
size. There's also
parser and not have to deal with different shells. But I will be switching from CMake, because it just does not expose what you want when you want it.
For me, the biggest issue was that on each platform you have different set of built-in kind of tools that you can use to build stuff, and they are configured very differently. On Linux, it's very diverse. On Linux, the only reliable way is to just have all of your dependencies included. But on Windows, it's common to install stuff, like the Visual Studio or Windows SDK. Those are stuff that you typically install. Or stuff like Ninja or CMake. Automat also needs them in its build process. I don't remember how I get CMake. Yes, I installed it from somewhere.
Hardware constructive interference size, which I'm not going to bother explaining right now. So we can just align as stood
Also
hardware
Clang
constructive interference
defaults
size,
to
and that will
default
ensure
linker being
that's some
compiler
size
board
that your platform has picked that is large enough to ensure that these things will be on different cache lines.
I'm
Alright, so
sorry.
going back to our concurrent bounded queue, that whole little tangent was just so that we could.
Yeah, so CMake doesn't use the LD.
replace std mutex in our concurrent bounded queue with ticket mutex, which is a lower latency mutex that performs well under contention and is also fair. All right. Now let's go and do talk about the termination detection mechanism that we need for our little task manager. And we're going to actually build the little task manager now. So we're going to call this thing bounded depth task manager. It's got a concurrent bounded queue. The item type is this any invocable thing. Just pretend that this is a std function. Std function doesn't support move only function objects. And I like all of my slides to be move only friendly. So any invocable is a thing that was supposed to go into.
This is nice, yeah. Putting std function is actually ties you to a very specific memory layout, because std function has some defined memory, and with invocable is a concept. You can pass pure lambdas into those templates.
To C++20, but missed the train. It was actually also supposed to go into C++17 and C++14. We keep deprioritizing it. A little unfortunate. But it's just a std function that works well with move-only function objects. So that's what this tasks member is. And then we've got a collection of threads using our little thread group thingy from before. We've got our thread function is this process tasks function here. It just looks like this. This is what each one of the threads in that thread group is going to run. So all it is just a while loop that while we've not received a stop request, we're going to dequeue tasks from the queue, and then we're going to execute them. That's the first set of parens here is for the dequeue. And then the second set, because whatever we've returned here is an invocable, the second set is executing that task. So it's pretty straightforward. And then this is just the constructor, which just passes a lambda that calls the process tasks function. All right, so now let's look at how we give work to this task manager. We have this submit method. It takes an invocable, so a function object or a function pointer, et cetera, or a lambda, and it just enqueues it into our queue. Pretty straightforward. So this is what using this thing looks like. We've got some atomic counter here that we're just using to have something to play with. We create a bounded depth task manager that has at most 64 tasks in its queue. We want it to have 6 threads in its task pool. And then we go submit 256 tasks to this thing. And each one of the tasks just increments this count by 1. But if you go and run this program, you might not see a count of 256 printed out here. Because at the end of this scope here, this bounded depth task manager gets destroyed. That destroys the thread group, which has a bunch of std_j threads in it. When those std_j threads get destroyed, they send a stop request to the underlying thread. And it's possible that one of those worker threads will see that stop request and exit before all of the queues are cleared. Or it's possible that all of them will see the stop request and exit before all the work has been processed. So we need, before those worker threads can actually exit, they need to make sure that the queues have been drained. So this is what we had before here. We just waited until we got a stop request, and then we stopped working. But that's not sufficient, because there might still be stuff in the queues when we get the stop request. So what we're going to do is we're going to add another loop after our main work loop here. And this loop is just going to, while we're just going to have a while true loop here. And then inside this loop, we're going to continuously try to dequeue things from the task queue. And as long as we keep succeeding, we're going to go and execute those things. And then once we're done, we're going to break here. So once we've drained the queue of tasks, then we know it's empty. And so we can go ahead and exit and be done. But there is still a bug here. A worker thread may block while dequeuing after all tasks have been completed, but before the stop request is received. So it's possible that like that the queue is empty, but that there's a worker thread who is blocked in this tasks.dq, and there's no more work coming, so they're never going to wake up. And so we're going to have a deadlock. That worker thread's just going to always be waiting for more work that's not going to be coming. So what we need to do here is we need to control exactly when all the worker threads exit the first loop. And we're going to do that using another new C++20 synchronization primitive, a latch. So in the destructor of bounded depth task manager, which is where we're going to shut down the system, we're going to submit a special task to each one of the queues. We're not going to, or to each one of the worker threads. Now, we can't actually submit work to a specific worker thread.
So in Automat, I'm just sending an empty task at the end. And this empty task reinserts itself.
And we know that none of these worker threads are going to execute more than one of these tasks because we're going to have them wait inside of this task here. So first, we're going to create a stood latch, which is a single-shot barrier. So a certain number of threads can all arrive at this thing, and once they've all arrived, then they will all proceed with their computation. So this stood latch, we're going to wait for however many worker threads we have plus one, because the current calling thread wants to participate in this barrier as well. So we've got a precondition that this destructor is not called from within one of the worker threads. That would be bad. This would blow up. So then, for each one of the worker threads, we will submit a task to the queue, and that task will just arrive and wait on the latch. So when each one of the worker threads dequeues this, it'll call out arrive and wait, and then it'll wait until everybody else has gotten there. And then, after this, we know that none of the threads have left that first loop yet. And so, or we know that none of the threads have left the first loop yet. Then we can send our stop request. And then after we've sent the stop request, we can release the barrier, the latch here.
Yeah, this is also nice.
So what we're trying to do is we're trying to hold everybody right here.
You can send a message that will block the
until
worker.
we sent the stop request.
And then resume it
And so once we sent the
yourself.
stop request, then we can say to everybody, hey, we're going to release all of you by arriving on this barrier. And then at that point, everybody will come out of this call. They'll then exit this loop. They'll see, hey, it's been requested that we stop. So everybody will see the stop request. They'll then go into this loop here that'll process any outstanding tasks. And then everybody will terminate, and there will be no deadlock. Yeah. So let's talk a little bit more about latch. So this is what the latch API looks like. So when you construct a latch, you tell it how many things you want to participate in the latch. And you can just arrive on a latch. You can just decrement the count on the latch. You can wait on a latch. And you can arrive and wait on a latch. And you can arrive and wait with a count that's greater than 1. The same thing for countdown. You can arrive with a count greater than 1. All right. So now let's go and find another way to break our little queue. So we're going to create this submit tree task, and what this task is going to do, it's going to increment some atomic. That's sort of unimportant. This count atomic here that it takes as a parameter. But then it's going to also take this level parameter. And if its level is not 0, then it's going to go and spawn 2 children tasks, each with a level that is 1 less than the parent task, that is going to also go and call submit tree. So this will spawn a binary task tree. And so like we use it here. We do a submit tree with a level of 8. So let's go and spawn a whole bunch of work here. So the bug here is that this code is going to deadlock, because this is going to create a whole bunch of tasks, and each one of these tasks is going to try to submit more tasks to the queue. The problem is that eventually the queue is going to fill up, and then submit will block because it's waiting for space to become available. But all of the other worker threads are executing these submit tree tasks, and what these submit tree tasks are doing is they're trying to submit work and waiting for somebody else to come in and clear out space in the queue. So like in this example here, we've got 6 threads in our task manager, what's going to happen is eventually all 6 of those worker threads are going to be in a call to submit tree, calling submit, blocked, waiting for somebody to come and execute work from the queue, but nobody's going to do that.
That's why it's good to have workers that specialize in CPU-heavy operations and avoid any sort of blocking operations. So a worker, quote, could delegate all of its blocking operations to some maybe other thread which will help with OS.io or this kind of stuff, and just try processing more items from the queue. Like it can start an IO operation, and this IO operation would reinsert the task later. This is how I'm trying to make Automat responsive and not get stuck. But it's a very fringe issue. It doesn't happen often. If you have sufficient number of tasks and you don't do crazy stuff like that, it does not happen. Something like this does happen in Automat, because in Automat objects can trigger multiple objects. You can have this avalanche of jobs.
What we need to do is what's called boost blocking. So when we want to block on some entity, we need to ensure that entity's we need to delegate the forward progress of our current thread of execution to that entity. We need to ensure that entity will eventually unblock us, that is. So one way that we can do this is instead of just submitting instead of just enqueuing our task here with a blocking in queue inside of submit, we can call try and queue repeatedly, which is a non-blocking mechanism, and then when try and queue fails, we can call this make progress function. And what this make progress function needs to do is it needs to ensure that space in the queue will be cleared up, because the condition for try and queue to succeed, the condition for us to make progress, is that we need there to be space in the queue. So how can we ensure that there's space in the queue? Well, we can go execute items that are in the queue here. So this is a little bit weird, because now we've taken our submit method, and our submit method might actually go and dequeue things from the queue and run those things.
But it's fun. It's a really clever trick.
It will ensure that
it converts the queue into stack.
Make progress. Now, there is still a bug here, because we might blow out the worker thread stacks with recursion, because we'll end up with on the stack we'll have a call to submit tree.
Instead of putting the work on the queue, this work item could just be executed directly. Make progress could just, if it cannot enqueue, just execute the function right away.
That'll be calling submit. That will be calling submit tree, because it'll be right here. Dequeuing thing is trying to make space for this submit call to succeed. And so then you'll have a bunch of these calls in the stack. But we're not going to worry about solving that bug. All right. So this is our bounded depth task manager. We've built our little mini runtime. So now let's look at what we can do with it. Let's build a couple little parallel algorithms. So let's start off by building a parallel histogram function. So this is first we'll look at what the serial implementation of histogram looks like. So histogram is going to take some input sequence, some output iterator. It's going to take a amount to increment each value by, and then it's going to take a mapping operator, which is going to take the value of each input element and index that value into the output sequence here. So the way that we implement this in serial, we just have this for each function.
The level of templates,
it just indexes into
I think
output
like more than half of this code is just templates, which they don't seem to serve any purpose.
All right, now let's look at a parallel version of this. And for the parallel version, we're going
synchronization aspect. This presentation is supposed to be about synchronization, not templates.
Input iterators are random access, or that the ranges here are random access, and that and we also added a execution policy parameter right here This is, let's just pretend for now that this is like a C++17 execution policy. All right, so here's the body of our parallel histogram function. So the first thing we want to do is we want to figure out, we're going to spawn off some number of tasks, each of which is going to handle a part of this problem. So we're going to go figure out how many elements are in the input. Then we will figure out how large we want each chunk of work to be. We're going to pretend that our execution policy has some magic chunk size function on it that tells us what's a good chunk size to use, what's a good granularity for the work. Then we need some way to synchronize all of these work items. So we're going to use a std latch
Some people
for this.
might call me crazy.
And then we're going to
In
go
FTL,
and create a
I
bunch of
dage
chunks. We're going to do that
enemies
by
out to
submitting
room
those
and
chunks
let
to
them
the execution
suffocate.
policy. So submit is
Works
just
on
gonna be some
almost
method on the
everybody.
execution policy that takes a task and executes it.
I think there are two races which are resilient to
and
this.
Inside of this submit function, we're going to go and compute the beginning and end of the chunk that we're currently executing. And then we're going to go call basically the serial version of the algorithm that we just saw a moment ago. We'll just go call it just locally on our chunk. So we just say for our chunk, just go and do the, compute the index for each one of the input elements, and then for that element in the output, go and apply the increment. Now, the problem here is that two different chunks
The one that takes oxygen
might
from room,
attempt to
and I
update
don't
the same
remember other
element in
one.
the output at the same time.
There
So
was
what we need is
also
we need our increments to
there are
output
also the
elements to
robots.
happen
There are
atomically.
those machines
We
that
could use a mutex,
also don't need
but,
oxygen, I
that
think.
might be slow. Or we could force our users to provide us with a sequence of std atomics as the output. But it would be a sort of unfortunate requirement if we said, hey, your output elements, they can't be just, T's, they need to be std atomic of T.
Plus, you could get extra
Because
scrap
this
because you
parallel
don't
algorithm,
destroy
the
shit.
parallelism should be transparent to the person calling this algorithm. So in C++20, we have another feature which helps us out here. It's called atomic ref. An atomic ref is a facility that lets you temporarily view any type of object as an atomic object here. So you construct an atomic ref by giving it a pointer to some other object. And then, as long as everybody else who is concurrently accessing that object is also using atomic ref, you can treat it just as if that object was a std atomic. So here we just declare a std atomic ref to whichever element is the one that we want to increment. And then we do a fetch add on that element here.
This is amazing. I had no idea about atomic
Here's
ref.
our parallel histogram implementation. So let's talk a little bit more about std atomic ref. So std atomic holds a T. Std atomic ref does not hold a T. It's a reference to a T. But otherwise, they have the same API. Another thing here, this algorithm currently, we're using fetch add, which means that this is going to only work if our output value type is an integer, because fetch add before C++20 only worked for the integer specialization of std atomic. But in C++20, we've now added std atomic floating point specializations. So now you can call all of the various math functions on atomics of floating points. So fetch add, fetch subtract, multiply, etc.
Now this is interesting.
And then,
Atomic floating
the final
points.
thing in our parallel histogram we call countdown on the latch, and then we block on the latch, but we don't block unconditionally. We call some make progress mechanism to ensure that we don't deadlock the system. And then in the calling thread, whoever launched this parallel histogram, we do the same thing. We wait for the latch to be ready, and we continuously call this progress mechanism until that happens. All right, now let's look at one more parallel algorithm, and then we'll be done. This one's a little bit more complicated. This is going to be a parallel implementation of exclusive scan. So exclusive scan is an algorithm that takes a range of values and writes the sum of the first n minus 1 elements into the nth element of the output. So each element of the output is the sum of all of the prior elements in the input. And so here, input is a range, output is an iterator.
That doesn't
is a
sound
binary function object.
parallelizable at all.
Might be like std plus. So this is somewhat similar to std partial sum, except partial sum would include the element at the nth position. Exclusive scan does not. So let's look at a little example of this. So suppose we have some array of 9 elements here, A, B, C, D, E, F, G, up to I. And so the exclusive scan of this would look like this. So
or maybe it is a little bit parallelizable, like with a tree, you know.
The initial value
You could compute sums of all those in parallel.
The first element has
and then
no
aggregate
prior
them.
elements to it. So the first output element is just the initial value.
Actually, this is a use case where
the
segment
second
3 could be used.
Is the sum of all
Provides
the one element
sublinear
for it plus the initial value. The third
initialization.
element is the sum of the first 2 elements and the initial value. All right, so how do we go about parallelizing this algorithm? So we're going to look at an approach that only supports non-commutative and non-associative operations, but that's the usual restriction that we have when designing these sorts of parallel algorithms. So let's start off by taking an approach similar to what we did for histogram, where we're going to take our original problem, we're going to split it up into chunks. So we'll split this up into 3 chunks. And then on each one of the chunks, we'll start off by running the serial version of the algorithm, just std exclusive scan in each one of these chunks. So for the first chunk here, we take ABC, we do an exclusive scan on that. That gives us, some unspecified value in the first element, then A and then A plus B. Same thing for all the other 3 chunks. Then we need to go and sort of figure out a correction that we need to apply to everybody, because we've computed a local value here, but this problem requires global knowledge. We need to distribute like this AB sum here. That needs to be included in the results for these 3 here, and in the results for these 3 here. And this DE sum here needs to be included in these 3 elements as well. So what we're going to do is we're going to take the value of the last element of each one of these local scans. We're going to add it to the last element of the initial array. So basically, we're going to compute the sum of each one of the chunks. And we're going to stick the sum of each one of these chunks into some array we're going to call aggregates. And we'll do this for each one of the chunks. So for the first chunk here, we end up with a value in this aggregate array of ABC. And then in the second chunk, we get DEF. And then in the third chunk, we get GHI. Then we're going to run an exclusive scan on this aggregates array. We're going to do this in serial on one thread. And we're going to add in the initial value at this point. So what we'll end up with in this aggregates array is X, and then XABC, and then XABC DEF. Then, going back to parallel again, we're going to increment all the values in each one of these chunks by their corresponding entry in the aggregates array. So all of the elements in the first chunk will increment by aggregate 0, which is X. Second chunk will increment by X ABC, etc. And then this gives us the output that we desired. So in the real world, there'd actually be a few more levels of hierarchy here. For example, if you were implementing this on an NVIDIA GPU. But it's simpler for us to just think about this in terms of these 2 levels here. We have a section of a first pass that's parallel. Then we do some aggregation calculations in serial. And then we go back to parallel to apply a correction to everybody. So traditionally, we call this first parallel pass an upsweep because the amount of parallelism is decreasing. And then we call the second pass a downsweep because the amount of parallelism is decreasing. In the upsweep here, we are taking information from everybody, and we're sending it to one guy. And then in the downsweep, we're taking the information that one guy computed, and we're sending it out back to everybody. All right. So unlike the histogram algorithm, we're going to implement this as a collective algorithm. So we're going to have this exclusive scanner struct. It's got the same parameters as the serial version. So it's got the input range, the output range, initial value, and some invocable. Those are just going to be member functions. Then we're going to have some constants that will compute in the constructor, the amount of concurrency, so how many concurrent actors are participating in this collective operation, the number of elements in total, and then the chunk size. Then we're going to have some this stood vector of aggregates that we'll use for the storage of the aggregates. And then we're going to have two synchronization primitives. One is stood barrier that we're going to call upsweep barrier, and then yet another latch. So stood barrier is a heavier weight version of stood latch. So stood barrier can do two things that latch can't. You can arrive at a barrier multiple times. Barrier supports multiple phases of arrivals. Latch, you can just arrive, like there's just one phase. Like everybody arrives and then it fires off and then you can't use it again. Barrier, you can use it to synchronize multiple different phases. And barrier also supports a completion function. So a completion function is this function that gets run by one thread at the end of each barrier, at the end of each barrier phase. So that the completion function, it takes on a construction in addition to taking the count of how many threads are participating in the barrier. And because there are multiple phases of a barrier, if you want to arrive at a barrier and then wait on it later, as you can with latch by calling countdown and then later calling wait, well, you need some sort of handle to the barrier to know which of the phases you're going to be waiting on later. And so instead of having a countdown method on barrier, we have this arrive method, and it gives you back an arrival token. And then if you want to wait on that arrival token, you give it back to the barrier when you go to wait upon it. We also have an arrive and wait, just like stood latch, and we have an arrive and drop, which is somewhat similar to stood latch's countdown. So arrive and drop is just like arrive, except it doesn't give you back an arrival token. This is useful because arrival tokens are no discard, because if you're asking for the arrival token, you need to do something with it. All right, so this is latch, which we looked at earlier. So the sort of comparing these two, both of them support asynchronous arrival. With barrier, it gives you back this arrival token. With latch, it doesn't need to. Latches are single phase, whereas barrier is multi-phase. Latches don't have any notion of thread identity. So a thread may arrive multiple times on a latch, and any thread may wait on a latch, even a thread that didn't participate in that latch. And latches don't have a completion function. Now, barrier does have a notion of thread identity. A thread may only arrive once per phase, and only a thread who arrives may wait. You can't transport arrival tokens between threads. And also, barrier supports completion functions, and that's the reason that we're using it right here. So we're going to use a completion function with barrier here. We're just going to use stood function in this case. And the thing that we're going to have this completion function do is it's going to do that serial phase in the exclusive scan algorithm. It's going to scan up this array of aggregates. So we've got a couple functions here. We'll walk through them. So that's the constructor. It's pretty boring. We just initialize the various counts. We compute the chunk sizes. We construct the barrier, etc. And then we have this scan aggregates function, which is actually pretty boring. All it does is it does an exclusive scan on this aggregates array. And it adds in the initial value at this point, as we discussed earlier. So now let's look at this launch member of exclusive scanner. So launch takes one of these execution policy things, and it's going to create a bunch of tasks in some loop, as we've seen before. So the first thing it's going to do is it's going to go and compute what's the range that I'm working with here, and then it's going to call this process chunk function on that range. And then again, we're using a latch here, the down sweep latch, to synchronize with all of the chunks that we've spawned. So the real meat of this is in process chunk here. So inside of process chunk, we get the index of the chunk that we're on, the range of input we're working with, and the range of output that we're working with. And so the first thing we're going to do is the upsweep. So in the upsweep, first we do an exclusive scan of the input elements, and then we wanted to get the sum of our chunk. And so the last element of the exclusive scan is the sum of all of the elements of our chunk except the last element, because it's the sum of all of the elements prior to the last element. So we just take the result, the last element, the result of the last element of the scan, and we add it to the last element of the input. And that's the value that we put into the aggregates array for our chunk. We don't have to do anything to protect access to the aggregates array because there's one entry in the aggregates array for each one of the chunks, so everybody can write to it independently. Then once we've completed the work for our chunk for the upsweep, we go and arrive and wait at the upsweep barrier. And after the last person arrives and waits at this barrier, then the completion function will run. So the synchronization semantics of stood barrier is you have in people arrive,
Zephyr Buick says,
then you have the completion function,
Hey, mate.
which happens after those people arrive, and then the waits complete only after the completion function has run. So you've got memory barriers on both ends of this. So before when we start executing the completion function, which scans the aggregates, we know at that point that all of the threads have computed their aggregate and they've written it into their chunk, into their slot in the aggregates array, and we know that we can see that value. And after we've completed the wait on this upsweep barrier, we know that the serial scan of the aggregates has been completed and that we can see the results of that. And so
This is very subjective, but for me, those barriers, they kind of obfuscate what's happening.
In the down sweep.
I mean, it's a nice primitive to have, but you have to use it a lot to intuitively know what it does.
For just each element of the output, we just add in the aggregates value for our chunk. And then the final thing we do is we arrive at the downsweep latch to signal to the guy that launched us that we're done. And this is
There is very little time left. I expected some
implementation of a working
benchmarks or stuff like that that would kind of show how
best way to implement
this compares
CPU is a slightly different algorithm, but that doesn't fit as nicely
to other approaches.
All right, so what did we talk about today? We talked about various enhancements to stood atomic, the wait notify interface, stood atomic ref, the test interface for stood atomic flag, floating point specializations. We talked about stood latch and stood barrier, two new types for coordinating groups of threads in C++20. Counting semaphore, which is a lower level, more general form of a mutex. And stood JThread, a enhanced thread class that has a joining destructor and that supports this.
I was actually curious how this parallel prefix sum compares with regular prefix sum. That's still very interesting. Okay, for some reason Skia seems to complain that it doesn't have size. Of course you have size. STD size, there it is. Yeah, size and data. Should take an array and give us a pointer. Maybe it's missing some include, like defined in header. Okay, defined in almost every header, apparently. And size is also pretty much everywhere. With container equal to int. Maybe this standard is not just strange. Including base HH. I can include base HH directly maybe, and now the error should shift. And from base HH I'm including what? Canvas. Just including canvas seems to cause the problem. If I do this, the issue is still there. How does this problem happen? I'm passing some container span. Okay, yeah. I shouldn't pass 2 here. Map vectors takes... what does it take? Okay, I have to run this with span. It should be implicit. Again, the same issue. Probably one of the overloads was removed. Okay, I don't need the last argument. I hope it's going to infer the proper size of glyphs. No, it does not. So it takes span glyph ID. What was the issue here? Okay. Actually wants those spans. Take this, then bounce. It's another span. Actually, no, this should be automatically cast into spans. Yeah, the API keeps changing. This should be map point now. Okay, it transforms. Those are very simple changes. Doing them is not a big issue. They are unlikely to cause any crashes. They're just a little bit annoying to do everywhere. There are more. I wonder if passing point is better than passing two floats. I thought that if you pass floats, they will somehow use floating point registers. I'm not complaining, it's a nicer API, but I thought it was deliberately done like that. The question is, will it crash now? I've updated Skia to the most recent version. Maybe I have to delete the precompiled version of Skia. Okay. While it's building, I'll be right back. If there is more linking issues, maybe I have to delete the Automat objects. Yeah, still have issues. Or maybe I know, Skia is built as a single library here. Let me see. How could this be missing? This was definitely compiled just now. There is no... this op... It's for path effects, right? It should be somewhere here. Path ops, okay. Okay, I need to add this as a new library. Yeah, very interesting. Can build it now, I think. Okay, we are getting issues with those blurs. We had them before as well, I remember. They used to affect this one as a lot. Okay, I can say that it doesn't seem to crash now. And it actually seems to be way faster now than it was. Skia seems to have changed something. Okay, there was a crash. It was way faster though. Weirdly. Have those options. So this issue has to be related to different recorders stepping on each other's toes. I have two different contexts. This background context and foreground context. Here I am creating them. I'm also passing some options here. I get different cues. I'm wondering, maybe I could enable some validation layers. That could help in tracking this issue down. It is annoying because periodic crashes make Automat unusable, so this is a high priority issue. It has to be fixed. Come on, crash already. Yeah, the strange thing is that this blur, it seems to be drawing over itself. I think the same issue that's causing this blur problem, it has to be the same thing that's also causing crashes. There's probably something that we are doing in a multi-threaded fashion, which we should not be doing in a multi-threaded fashion. That's clearly causing issues here. Come on, crash already. Like, when debugger is attached, it just doesn't want to crash. Oh yeah, there we go. The same issue, address not mapped. This is probably, yes, a very small address. But now we have some more information. Probably some of the compilation options are different now, so we'll get access to everything. Inside this I don't have access to those variables. Optimized out. Optimized out and overwritten by signal handler, I guess. I mean, VS Code should be able to recover those registers from signal handler. Because in signal handler, those registers, they should be accessible. OS, when there is a crash, it captures the current registers. That thing should be there. Okay, so none of this we have index here. Geometry uniform tracker, write uniforms. Okay, we have been recording timeline. And the recording for timeline, apparently we are still using some image filters. So this geometry uniform tracker, according to this dump, has last index set to 0. So if index equals last index, it should return false. Last index equals 0. Form key. It is some kind of bit set. Okay, so that index will be 0. Bits 1747 of this key are 0. Okay, so maybe last index was not 0, but it was changed to 0 as a result of something. So maybe this is caused by this. Layer. Actually, no, there is no splicing. There is no layer here. It's also inactive. Inactive. Splicer. Could this drop shadow cause issues? Maybe. thing is, when those things happen in different objects, because this usually happens in timeline, but sometimes it happened in those keystroke objects as well. The issue tends to lie elsewhere. So those may be red herrings. Those crashes, I mean those call stacks. Come on, start up. I want this to... I want to stress the animation. Let's animate as many objects as we can. Okay, there is this display. This display has a shadow. This is another image filter that could be causing issues. This draw background. Again, very small value. It's the same type of crash. Where are we crashing now? In hotkey. Hotkey should be rendered in foreground. Drawing some path, sure. And that path has some image filter. There is the recorder. Unique ID 4. Okay, there is a bug. I mean bug is a to-do in Skia source code. I wonder why are we twice on the stack trace? It's some anomaly from compiler. This device is calling internal flash. Device, if I understand correctly, it's more like a layer in an image. Those devices, it looks like they are very ephemeral. This is just an interface, a device. DSC, draw context. I actually wonder which part of this call hierarchy is shared between threads. I wonder what are other threads doing. This one, order 0, is currently locating memory. So this is drawing key button. The one that crashed. This one is also allocating some memory. Is doing key label widget. This one is doing key. Key button, and this one, they're all busy allocating memory. Another key button. So this one is doing some memory allocation. The same. I'm pretty sure that if I decrease the number of renderers, the issue will go away. If I increase it, it will go up. So if I changed it to, like, how many threads do I have? Yeah, I could go with 12. With 12 it should happen faster. Also, more of those. Interesting. So with 12 threads, it seems like it doesn't want to crash. It's Tracy showing us here. Select all. I just want to see recorders. most of those renders are very, very fast because we are not doing anything really. I will log more stuff. DK recorder thread. Let's do a scope here. It has to be a constant string for this to work. This is what I want to include. It says that it's not going to work, but it will work. There's no such thing as zone name. Do zone text. Yeah, by this shadow I can tell something is not right. This shadow shouldn't produce this effect. It's weird that it happens less frequently now, the increased concurrency. It's a nice histogram for how long it takes to execute this function. So how long it takes to record a single image. So this is what all of the threads are doing. Timeline is definitely the slowest to play back. There's also root machine here. This is actually a lot of work which is being parallelized. It's actually pretty sweet. Okay, why do we see those artifacts there? Now we have just one recorder thread. If I attach Tracy and zoom, disable those ghost zones. Oh, I can do some fancy zoom in and out. Now it looks like all this recording takes far less time, and this still seems to happen. Huh. Problem stopped happening. The clip doesn't work. No idea why. Okay, this should be 7 mm. So many strange issues. Seems like this clip has no effect on the background texture. So it doesn't affect the clip, but it seems to affect the path. I wonder if the bug build will also have the same clipping issue. Oh, it needs debug. Yeah, okay, it's going to take a while. So, ideas. What could I do to fix those crashes? So enable Vulkan validation layers. Possibly. I could try to trigger the crash in debug build, but for some reason it doesn't want to happen there. And also when I started changing the number of threads, the issue also went away. Same I can say for 12 threads, they also somehow seem to work. But four threads seem to crash. Yes, on the back build it doesn't crash at all. But here I will put some question marks because I'm not 100% sure of those things. Performance is excellent in graphite. Performance is not the issue. The issue is results. Okay, we are compiling now. So many strange issues which are appearing and disappearing. There is this weird clipping issue. Okay, it still happens on debug builds. At least there is that. I will change this to just 4 centimeters. I just want to see if it's possible for me to clip. with rounded corners. There is something here. Maybe it's clipping correctly. If I increase the radius. I want to see those rounded corners. Otherwise it seems that clip rect is broken. Yeah. Could we increase this even more to 4 and 4? Still. Remove that case. Nope. Okay, this clipping creates an issue. So there is this corner clipping issue, and there is this text field which sometimes works, now it works, and sometimes it doesn't. So if I increase the number of threads back to 12, should we see it again? Or maybe I need to pass through here. Maybe it thinks this is subpixel, because I'm using very small values. Yes. Yep. And also this issue came back. Yeah, it was here just now. Okay, so in all places where I have clip rect, I should be now super careful because Skill assumes that I'm working in pixel space here. Yeah, the issue is fixed. So this is a single 16 millisecond frame, and this is what we have been recording. A lot of widgets being re-rendered, essentially. How do I keep environment? Capital E. What was this thingy? Okay, the reason I started this as a root is that when I connect with Tracy now, Tracy can give me more accurate access to the stuff that CPU is doing. And unzoom. Hide those. Now in Automat I can do some fancy zoom in and out. And now I can see not only what each recorder thread is doing, but also how the locking between them works. This one was recording key button and then key label widget, but this key label widget was... There's a lot of locking between them. It's a render thread which was still doing something here, apparently. So within this frame, there is a very small section that we actually parallelized. There is this section at the end, which is totally not parallel, and there is this section at the start, which is also not super parallel. I mean, the fact that crashes are gone is a little bit nice and a little bit annoying. And what's with letter spacing? Why the letters are touching? It's another issue. Okay, I feel like I'm not progressing at the moment. This one is away. but crashes are still an issue. I will take a look at them. So for today, this is it. I will try to work on reproducing those crashes. Yeah, and I'll see. On the next stream, we'll either try to attack this issue, maybe trying some of those things, or finish the mouse recording stuff. Actually, splitting is not probably that necessary. Probably nice to do it anyway. Anyway, this is it for today. See you next time. Bye bye.